We are now entering into the magnetic field topics, and we want to focus on the point charge. As usual, we'll start with the simplest possible structure, and then we'll build up complexity from there. We have to appeal to your acceptance of the electric field. It's just out there. We know it's there. We've measured its effects in the first 7 weeks of this course. Now we're adding the existence of another vector field quantity. This we call the magnetic field. We use the symbol uppercase B, vector, because the letter B is present in the word magnetic. The units of magnetic field are called the Tesla. Use the symbol capital T. Just like the coulomb is a large amount of charge and the amp is a large current, the Tesla is a significantly large magnetic field. The sun is constantly trying to kill you. One of the nice ways that the Earth protects you from the sun is with a rather large magnetic field. We know that magnetic field of the Earth has changed its orientation throughout the history of the Earth. If you look at magma, which has frozen into the bottom of the ocean, there are magnetic materials that have frozen in place to match the orientation of the Earth's magnetic field when the magma came up and solidified underwater. So we see that flipping back and forth over time. And of course, on geologic timescales, we are due for another spin flip in the near future. When these death rays from the sun, they're primarily just protons. When they're accelerated from the sun, they come to us with some significant velocity v, and they encounter the strong magnetic field of the Earth. There is a force which deflects them up around to the north and south pole, giving us the northern and southern lights. That force, which we'll label FB to distinguish it from the FE electric force, is a vector. It is the vector product of the charge Q. You must include your plus or minus signs. The velocity vector V in what we call the lab frame, that is, everyone in this room will agree on the motion or velocity of the charge with respect to us. And the cross product with the magnetic field vector. So we have Q, V, cross B. Just like with torque earlier in the course, we need to make sure that the order of these vectors in the cross product is preserved. Of course, if you flip the order, you pick up a minus sign. So if your velocity is at an angle theta with respect to the B field vector, in this situation, your cross product by the right-hand rule points out of the page. In magnitude, that force will be Q magnitude, speed V, magnetic field magnitude B, times the sine of the angle between the vectors. Of course, we're just applying the usual right-hand rule for cross product. Any vector A crossed with any other vector B gives you your cross product C. Your fingers represent the first vector in the product, A, your palm direction, B, your thumb direction is the cross product. Some of you learned it this way. That's just as well. And we'll use some three-dimensional models in class to solidify the vector orientations in your mind. Of course, if in this situation v cross b was out of the page, if you're dealing with, say, a proton, then the force would also be out of the page on that particle. But if you were dealing with an electron, the force would be into the page because of its negative sign. This implies that the magnetic force, Fb, is always perpendicular to the velocity of the particle, the charge, and it's perpendicular to the magnetic field B. Another way of saying that is the force will always be perpendicular to the plane which contains the velocity vector and the magnetic field vector. If you look at the work which is done by that magnetic force on the charge during any trip, you notice that the dot product of magnetic force with your dl vector in the direction of velocity, that's always 0. That dot product has to be 0 because your force is perpendicular to the direction of motion. We conclude that the magnetic force cannot do work on a charge. However, it can change its direction. It is a force, it's clearly going to produce an acceleration on that charged particle, but that acceleration will always be perpendicular to the velocity at any moment. The acceleration vector perpendicular to the velocity vector will change its direction, but not its magnitude. That will be an important conclusion that we use in class when we analyze circular motion.